Welcome to CE 3305. We're now getting into Euler's equation and Bernoulli's equation, which I believe is chapter 4 of the book. We'll go pull up a copy of the book in a second and verify that. Euler's equation of motion. And then there'll be Bernoulli's equation for pressure variation. And it will be a little bit of a hand wavy on my part, but actually Bernoulli's equation comes out of Euler's equation for a certain model of energy loss when we set the time derivative part of Euler's equation to 0. But let's not dwell on that right now. That's kind of getting ahead of ourselves. We're also going to look at Lagrangian and Eulerian points of view. As in the context of the variational calculus as applied to fluid mechanics. So we're going to start this whole thing off with flow patterns. And what I'm actually going to do is I'm going to go away from the draw pad in a second, and I'm going to pull some YouTube videos and just watch a few seconds of them. And more importantly, you'll be able to get the reference to find them on your own. So we're worried about real fluids. And in real fluids, markers such as dye, smoke, heat, and similar things are used to visualize how things flow. Even today they're used, although the world is going to more and more computational fluid mechanics. It has more trust than it used to. The technology's changed. But occasionally flow patterns and actual observations are used to validate that the computer response is faithful to the real response. These markers are called tracers, at least in many instances. And the tracer hypothesis is that the tracer moves with the host fluid. And doesn't interact with it or doesn't change its properties. Now, at some scale, that obviously can't be true, so anything that's in the fluid is going to affect it. But from a practical sense, many things satisfy the tracer hypothesis in practical cases. We're going to look at timelines, path lines, streak lines, and streamline. Now, many of these look identical in flow systems, but they have a particular meaning in the calculus part of fluid mechanics. So a timeline is a line that's formed by marking adjacent fluid particles at some instant, and we'll see a video showing that. A path line is the trajectory that a particular fluid particle would take. So if you could attach a blinking LED to a fluid particle and then had a video screen that could keep track of the blinking LED over time, the path that LED draws would be a path line. A streak line is the trajectory of many particles that all pass through some common point in space. A streamline is a line in a flow field that's tangent to velocity, and no flow can cross a streamline. So streamlines have some important, both practical and theoretical implications. So let's take a look out here and see if I can find the YouTube videos I'm interested in. I happen to know that at rtfmps.com, backup website, fluid mechanics, links to cool videos. Now, we're not going to watch the entire 35 minutes. I just want you to be aware of the existence of the video. So this is from a while ago.
Visualization, solution of engineering problems, and also as an aid to understanding the concepts of fluid motion. We ignore them in observing the flow pattern.
So here's a
Here you see a probe with multiple thin fingers, which makes many fine lines.
so
Another
each of
kind
those
of
is
probe is a
producing
single wire with sections insulated so that we see bands of bubbles coming off the probe. Instantaneous location of a line of fluid particles. Often it is useful to use multiple streak lines to observe a flow field.
So those are
You
streak
can make
lines.
them with the multiple finger wire you saw before. The third concept we need is the timeline. A timeline is defined as the instantaneous location of a line of fluid particles marked earlier at a prescribed location in the flow. These lines are usually most useful if the marking location is normal to the flow direction, since then the location of the timeline, a short time later, shows the velocity profile of the flow field.
Okay, so these videos are available for you. I've got them all cross-linked in this URL, and that should be valid for the duration of this class. At some point in the future, all the videos will get moved onto my Moodle server, but for the time being, they'll be here for a while. Here's another one on visualization. Oh, I bet it's the same one. Yeah.
Location.
There's a nice one on vorticity that will come in handy. So there's quite a bit of videos that are perfectly legitimate in the context of this course. Let's return to the drawbarian. And I'm going to draw a sketch and then describe parts of it. So imagine we have a vessel. You can think of it as a bucket, only we're looking at a cross section. And then we have a little nozzle out the bottom. And we're going to fill this bucket with a fluid. Fluid will be this blue. And we'll fill it in such a way that as liquid leaves the bucket, it's replaced so that the free surface up there at the top doesn't change. And this is actually achievable in practice. It's possible to build such situations where you can maintain a constant head. Okay, so there is our system. We'll have a free surface up here. It's blue because it's water. And now let's imagine we mark particle in red. Now I picked the middle on purpose because as time progresses, it's going to move this way. And exit the system. It's going to follow this path. So that happens to be a path line for all particles that start up here. In addition to being a path line, it is also a streamline, and as the fluids replenish, there could be many and many of these, so it's a streak line. Let's look at one that's over here by the edge. Now there's no reason for it to go that way. It's going to also try to follow that, but at some point, in order for the continuity to be preserved, it might do something like this. Similarly on this side, you might have another one going like that, and I'll try to draw an intermediate one. Alright, so this is, as I just said, this is a streak line. Happens to also be a path line. And it happens to also be a streamline. And bear in mind the flow here is steady. So in steady flow, this is usually going to be the case. Streamlines, streak lines, and path lines are coincident. They're indistinguishable from each other. In unsteady flow, they can be different. The streak line, path line, and streamline can all be different. Now, we want to ask ourselves in the sketch, is this a uniform or a non-uniform flow field? And we would have to go back to the book and read what the definition is. And the definition is a uniform flow field is a flow field where velocity does not change along a streamline. So the velocity doesn't vary much with position along that streamline. Non-uniform flow is where that is not true, where the velocity varies with position. So let me put a dashed line right about there. And I'm going to ask you to do a experiment with me. Down in this region, remember velocity has both magnitude and direction. So there's the velocity of that fluid particle at that point. And not too far away from it, there's the velocity of that fluid particle at that point. And here it is at that fluid particle at that point. So clearly, the velocity is changing at least in direction, if not also magnitude. And in fact, it's doing both. So this one should be shorter than that one. Up here, however, it's not too hard to conclude that the velocity is pretty much the same as we're moving through the flow field. And the indication of that is actually that these streamlines are parallel. They're not squeezing together or spreading apart. If we were to draw a timeline, label everything green at that time, wait a little bit of time, green would be here like this, wait a little bit time more, green would be here like this, and then that dashed line is essentially where I'm moving from uniform flow to clearly non-uniform flow. The green line is going to start to do that. I'm doing this, taking a lot of artistic license here. Those aren't necessary at the same time. It actually is going to have to accelerate to get out this hole. So above here we have uniform flow, and below is non-uniform. And both are quite common in practice. Now let's examine the velocity field. So there's a Lagrangian and a Eulerian point of view. In Lagrange's point of view, we consider an individual particle. In Eulerian, we consider a location in space. Back in your other engineering mechanics classes, when we talked about systems, things behaved as rigid bodies or points, that was largely an implicit Lagrangian statement because it gave us, we had tools to analyze that. Fluids are can be a little bit more complicated because we often have to switch between the two referencing systems. Flow dimensions are classified by how many spatial coordinates are required to specify the velocity field. So when we talk about one-dimensional flow, that means one spatial dimensional captures most of the necessary information to describe the flow. Two spatial dimensions might have an x and y coordinate, and then three would be x, y, and z. Now all real flows are 3D, but useful engineering analysis is often possible with two-dimensional and one-dimensional approximations. If we look on page 121 of the book, it has a nice discussion of this dimensionality that I just mentioned. All right, let's look at a reference location up here in our fluid, and we'll make a little more, I'm only going to look at a portion of it. And we have our particle right here at point A, follows some kind of path. Here's some other point, and we can pick some reference system rigidly fixed to the planet, a nice inertial reference system, and we can measure from this reference point, let's call that O, the origin, to point A, and we would have a position vector. I'll use the symbol r, and that position vector can change with time. We know that here we have position vector at t2, and we'll go ahead and have one right at the exit. There's our position vector r at t3. Let's call that t1. So we have A, B, C, which correspond to 1, 2, 3. Oh, that's very Jackson 5 of us. Now from our mechanics class, we would define the velocity of that particle. So I is referring to the particle, so this is particle I, is the change in the position vector for that particle with respect to time. Velocity is dx dt. This is a Lagrangian definition. We can now expand the r in terms of x, y, and z coordinates, since that's what we're fairly familiar with, but we can't do it on this sheet of paper because I'm out of paper. Oh, do I have any? Oh, here's some blank paper. Excellent. Party time. Excellent. So the velocity of each particle is expressed, when it's expressed all at once, that mathematical structure is called a field, and it's called the velocity field in this case. And field is just from the mathematical description for a field. So for our ambitious little particle, we have r of t is equal to the position ti plus position ti j plus position t k, where I, j, and k represent unit vectors in the x, y, and z coordinates, and x, y, and z represent the particle's coordinate position at some time t. So this is a parametric position vector. And the parameter in this case is time. The velocity vector, by definition, is v is equal to dr dt, which would be dx dt at time t I plus dy dt at time t j plus dz dt at time t k. And that might be some functional form. So this term is a velocity field when we consider all the different possibilities it can take on. So there's a lot of fields we encounter in engineering. And the advantage of them for this is that there's a lot of integral rules that can be applied to fields, and these are going to be used later on. We have magnetic fields, electric fields, gravitational fields, velocity fields, and there's other things that can be fields. The key thing here is that if you know the location, you know the behavior. Okay, sometimes, well actually most of the time, we substitute the letters u, v, and w for the dx, dy, and dz, dt terms. So u of t equals dx dt at x, y, z, and t. V of t equals dy dt evaluated at x, y, z, t. And w of t equals dz dt at x, y, z, t. Now this is seemingly complicated because it's looking like we're trying to use every letter in the alphabet and a few that haven't been invented yet. But this has some attractiveness in that mechanistically these are bookkeeping exercises, just keeping track of where a particle is and how it moves. We'll look more on Lagrangian and Eulerian reference frames around pages 116 and 117. They do a really nice job of comparing the two reference systems. So the velocity field could be represented in Cartesian coordinates, as I've done here, but the other thing is called a path line coordinate. And it too is often quite valuable, especially for Bernoulli's equation. So if we're in a steady flow field and we know the path a particle is going to take, we can establish an origin somewhere on that path. And because the particle is going to follow that path, we can instead keep track of distances along the path, so that it'd be S1, S is supposed to represent the arc length function, S2, S3, and so on. And then we can describe the behavior of that particular particle with a tangential velocity and a transverse or a normal velocity, normal to the path line. And this can be done in 2 or 3 dimensions. So x, y, z, that might be our Cartesian system, but in the path line system, it's going to be distance along the path from its origin, and there'll be a u velocity along the path, and there'll be a velocity transverse to the path. For use of this concept, we need to know, so for tangential and normal, we need to know the path. It's usually obvious where you can apply this. Certainly, for example, a pipe, you know the path the water is going to take. It's going to go down the pipe. and so tangential and normal might actually make sense. And where it's obvious, the pathline coordinate system is often a superior analytical tool. So some examples of uniform flow that we see in everyday life. So uniform flow, based on our word definition, would be that the change in velocity along the path line, evaluated any position, is equal to 0. So along the path, no change in velocity. So that should be, so if it's going down a pipe, if it's moving at one speed at one end of the pipe and the same speed at the other end of the pipe, there's been no velocity change in the path line system. So uniform, and that's called uniform flow. And that occurs in things with relatively straight path lines and constant cross-section geometries. So some simple examples. A pipe. Pipes are really easy to draw. Two parallel lines. A little bit of shading to indicate that it's a material boundary. Fill it with water. There's my little water pen. There it is. And now we have total discharge, and the path lines are parallel. Now they may take different cross-sectional geometries. For example, in turbulent flow, the velocity field looks something like that, whereas in laminar flow, velocity field is much more parabolic looking. And actually, when you plot them on real plotting paper, it's very challenging to tell them apart just by looking. We can also have flow in a channel, like a river, and those are easy because you only have one material boundary. Upper boundary of flow is the free surface. You notice I put it on slope, so we have something to drive flow downstream, and again, relatively parallel. Path lines, generally velocity distributions in streams kind of look like that. But we often do our analysis as if it's uniform in the vertical. And then the last commonest thing I can come up with would be a aquifer, make a nice confined aquifer. So there's one layer of geologic material up here, black slicky rock. Beneath it is green rock. And then aquifers are full of solids and holes. The little red dots are supposed to represent the aquifer materials. And then the water flows in the interstitial spaces between the solids. And again, based under many conditions, we get nice parallel flow. And usually aquifers, for the most part, the velocity profile is going to be look something like that. It's pretty much almost a straight line. That's because the component of velocity is pretty small in a porous media flow. So we take advantage of that and pretty much assume this profile. If the geometry changes, like in a nozzle, then we would get non-uniform flow. So go back to our pipe, turn it from a constant cross-section to changing cross-section. Fill it with water, and we might have it coming pretty uniform in like that, but the water has to accelerate to get out of here, and so the flow lines would start doing something like that. It's hard to draw. Uniform, 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 non-uniform. There's also laminar and turbulent flow. So laminar means layers, and then turbulent is not layers. Laminar flow is where the fluids in adjacent layers move smoothly with respect to one another. Turbulent flow is the opposite of that. The layers, the fluid mixes between these layers, if you will. So there's quite a bit of mixing, and fluid and turbulent flow can be on one edge, and then a very small fraction of space and time later be completely somewhere else. There's also the concept of viscous, and non-viscous, I-N-V-I-S-C-I-D, flow. In viscous flow, shear stresses influences flow, and in viscous flow, shear stresses are so small that they can be ignored. Now, all real fluids are going to have some viscosity, except maybe, I don't know, supercooled helium might not. But everything else that we encounter is going to have viscous properties. But many practical cases, we can neglect the contribution of viscosity and get a meaningful and useful analytical tool. So in viscid flow, although theoretically it's satisfactory and in practicality doesn't really exist, it's a very useful model of nature, and so it will get used quite a bit. Okay, we're going to take one more drawing to draw some other things. So this is supposed to be a cylinder and not some sort of weird. That was supposed to be a circle. That didn't come out so good. And we can have flow approaching it, and it may hit this point. It's often called a point of stagnation. Actually, we're going to have the flow come in blue because the colors are going to matter. And we can have a boundary layer that forms on the surface of this sphere. At some point, that layer will separate and start to fall apart. Flow separation. Now that doesn't mean that the fluid actually separates from the solid object, but the flow field, this boundary layer detaches, and so fluid has to come back in from behind to fill the space. And it's obvious, to me at least, that that's how you get a lot of drag, and that's why bicycle riders and birds and so forth draft each other, because then the lead object does most of the work on the flow separation, and the other objects get to fly in this wake. We move a little bit away from it, and the flow is disturbed, but not necessarily separated. And further away still, the disturbance becomes less apparent. And then far enough away, the lines are all parallel. In this drawing to the left, I have implicitly assumed that everything there is nice and parallel, and so this is inviscid flow. And then this is not the case, and we would have to look at boundary layer, wake, and potential flow regions to describe this. So this drawing gets many different flow regimes. There's the approach I've assumed is nearly inviscid. There's a boundary layer with a viscous flow along the wall. There's separation where the flow leaves the wall. And there's a wake, separated flow behind the body. So the drag force goes up when there's separation. It's impossible to prevent this, but there are tricks that can be used to modify the behavior and change the flow regime. So I'm going to put a photograph in here to illustrate that. So these are 2 bowling balls. This was done at the Office of Naval Research a long time ago, back when cannonballs were used to make ships go to the bottom of the sea. And they're both falling into water, and they're at their moment of impact, they both enter the water at a speed of 25 feet per second. That would be about 20 miles an hour. You wouldn't want to get hit with that. It would cause massive damage to your dignity, not to mention your body would have holes in it. This one on the left, has a smooth boundary layer, and the layer separates just a little bit below the equator of the ball. And this one actually has quite a bit more drag, because if you were to look at this arc, it's going to push that water out of the way. By putting a little bit of roughness layer, it's called a sometimes called boundary layer trip wires. They're used in aircraft and other things. So the flow separation here was at the equator. Here it's behind the equator of the ball. And the cone, the amount of water it's having to push out of the way, the cone is smaller in diameter. So there's slightly less drag in position B than there is in position A. And so this boundary layer effect is a big deal in many objects. One last cool thing, and then we will conclude the video. I have a little fluid mechanics flow simulator that I'm booting up right now. And we can see the effect of flow disturbances in various cases. So what it is, it's a computer program, runs on a phone. All it does is make pictures. But we'll go ahead and we'll let nice, steady, uniform flow occur, and we'll see all the streamlines are parallel, and then we'll introduce disturbances into the flow field. Okay, now let's see if I can get this to work. All right, we're going to kilobytes. There we go. So I'm going to attempt to zoom in now. There we go. 2x zoom looks pretty good. Okay, so here's a flow field. And see, currently we have it doing particles. We can have it representing it as smoke traces. It isn't very interesting. It can draw a pressure field, speed. Let's go back to particles. And we can insert particles at different positions. And so now what we're producing are path lines. I believe we can erase lines. Nope, don't know how to do that. I don't care about that. And it confuses it a bit when I do that. Okay, and then we get it back to, okay, so here's our particle field. And now I'm going to draw something solid like that bowling ball. So let's compare it to the two pictures, and there's quite a bit of commonality. Here's the inviscid flow at the approach, and then there's a wake. Now this particular simulator, I think, has some random number. You can see how some of these particles get stuck on the backside for a while. We can change the shape. Go to a box and get a much different wake, which is why when you're drafting vehicles on high-speed bike riding, you want to go behind a van, not a motorcycle. No, that's not what I want. I want to actually get draw. This thing will not work, will it? Go figure. So flows are going to be moving up. A box like that. If we put one behind it, it doesn't do much interesting, but if we put one out here in the free stream, then it starts to bug things up. So this is just a little computer program to, it's a toy, but it will give you an idea of the effect of hard objects in a flow field. Let's do one more thing. Let's build a pipe. So a pipe has two walls. So here's our pipe walls. And even in this silly little program, we see that the flow in the pipe is essentially uniform, unless the pipe starts to get rough spots and the flow is disturbed, and that's what causes friction. All right, that concludes this video.